Welcome students to the MOOC lecture series on advanced probability theory. This is lecture number 15. In the last class, we have seen moment generating functions and some properties of it. These are important because of the uniqueness theorem, which says that the moment generating function of a distribution is unique, that is corresponding to each random variable there can be at the most one MGF. I am saying at the most because there may be distributions which do not have the moment generating function. Therefore, each moment generating function can be associated with one unique distribution. The advantage of the uniqueness theorem of the moment generating function is that if we identify the pattern of the moment generating function for some variable x, then we can identify its distribution. For example, suppose x is binomial n comma p, therefore, MGF of x at t is equal to q plus p e to the power t whole to the power n. Suppose y is distributed as binomial MP, therefore, MGF of y at t is equal to q plus p e to the power t whole to the power m. Now, suppose x and y are independent, therefore, MGF of z is equal to x plus y is equal to, we know that is the product of their individual moment generating functions, that is q plus p e to the power t whole to the power m plus n, which is the MGF of binomial m plus n comma P. Therefore, we can see that the sum of two independent P and binomial m comma p is distributed as binomial n plus m comma p. This is one result we have proved earlier, but now we can find very easily. In a similar way, suppose x is normal with mu 1 sigma 1 square, therefore, its MGF at t is equal to e to the power mu 1 t plus half sigma 1 square t square. Suppose y is normal mu 2 comma sigma 2 square, therefore, MGF of y is equal to e to the power mu 2 t plus half sigma 2 square t square. Therefore, if x and y are independent, then MGF of x plus y at t is equal to their product, and it is equal to e to the power mu 1 plus mu 2 t plus half sigma 1 square plus sigma 2 square into t square. That is, x plus y is distributed as normal with mu 1 plus mu 2 and variance is equal to sigma 1 square plus sigma 2 square. Again, a result earlier we proved by convolution, but now get very easily. Let us now focus on some deficiencies. For example, consider Px to be a PMF of the following form: Px is equal to 1 upon x into x plus 1, x is equal to 1, 2, 3. Therefore, sigma Px x is equal to 1 to infinity is equal to which is equal to 1 minus half plus half minus 1/3 plus 1/3 minus 1/4. And if we notice that alternating terms keep on cancelling, therefore, this is going to be 1 as the sum goes to infinity. Therefore, this is a valid PMF. Therefore, what is the expected value of x? This is equal to sigma x upon x into x plus 1, x is equal to 1 to infinity is equal to sigma 1 upon x plus 1, x is equal to 1 to infinity is equal to half plus 1/3 up to infinity is equal to sigma 1 over I is equal to 2 to infinity, and we know that this is a divergent series. Hence, its first moment does not exist. Another example, x is a random variable which takes values 2 to the power 0, 2 to the power 1, 2 to the power 2, etc. with probability of 2 to the power n is equal to e to the power minus 1 into n factorial. Therefore, sigma p x, x is equal to 0 to infinity is equal to e to the power minus 1 into 0 factorial plus 1 upon 1 factorial plus 1 upon 2 factorial plus etc. is equal to e to the power minus 1 into e is equal to 1. Therefore, it is a valid PDF. Therefore, its MGF is equal to sigma e to the power minus 1 x factorial into e to the power t into 2 to the power x, x is equal to 0 to infinity. This sum does not converge for any t greater than 0. Therefore, moment generating function does not exist. Like that, we can show many examples where there are problems with respect to MGF. However, MGF is important because of its uniqueness. Hence, a natural extension is to compute expected value of e to the power I t x, that is expected value of cos t x plus I sin t x. Since e to the power I t x is a complex number, therefore, modulus of e to the power I t x is equal to 1. Hence, this series obtained from expected value of e to the power I t x, that is expected value of 1 plus I t x plus I t whole square upon factorial 2 x square plus I t whole cube upon factorial 3 x cube, which is equal to 1 plus I t times expected value of x minus t square upon factorial 2 expected value of x square minus t cube upon factorial 3 x cube. Like that, we get an infinite series. This always converges. This expectation of e to the power I t x for a real number t is called the characteristic function of a random variable x, which we often write as phi x. Since we have already computed moment generating function for different random variables, we can easily find that characteristic functions of different random variables as follows: binomial n comma p, it is going to be q plus p e to the power I t whole to the power n Poisson lambda is equal to sigma e to the power minus lambda lambda power x upon factorial x e to the power I t x is equal to sigma, say x is equal to 0 to infinity e to the power minus lambda lambda e to the power I t whole to the power x upon factorial x is equal to e to the power minus lambda into e to the power lambda e to the power I t is equal to e to the power minus lambda into 1 minus e to the power I t. That is the characteristic function of Poisson random variable. Similarly, for exponential random variable, this is going to be 0 to infinity e to the power I t x lambda e to the power minus lambda x dx is equal to 0 to infinity lambda into e to the power minus lambda minus I t x dx is equal to lambda upon lambda minus I t. Finally, for normal mu comma sigma square, its moment generating function is mu t plus half sigma square t square. Therefore, here we should get half sigma I t whole square is equal to mu t minus half sigma square t square. Okay, friends. In a similar way, we can calculate the characteristic function of different random variables. Again, like the moment generating function, the characteristic function is also unique, and given any distribution, it will have a unique characteristic function, and given any characteristic function, it should correspond with one particular distribution. One particular distribution where it is very useful is Cauchy distribution. X is distributed as Cauchy with 1 comma 0 if f x is equal to 1 over pi into 1 upon 1 plus x square. Its more general form is C r comma mu, and its f x is equal to 1 over pi r square plus x minus mu whole square. For this lecture, we shall stick to C 1 comma 0. Since, so I missed a point, let us write that minus infinity less than x less than infinity. That is, it is defined over the entire R. Since integration minus infinity to infinity 1 over pi 1 over 1 plus x square dx is equal to 1 over pi tan inverse x from minus infinity to infinity is equal to 1 upon pi into pi by 2 minus pi by 2 is equal to 1. Therefore, it can be considered as a PDF. So, what is his expectation? One over pi integration minus infinity to infinity x upon 1 plus x square dx. Analytically, it is not convergent, but for most practical applications, consider with the principal value which is equal to 0 and therefore, you often find that expected value of x is equal to 0. What about expected value of x square? Expected value of x square is equal to 1 over pi minus infinity to infinity x square upon 1 plus x square dx is equal to 2 times 0 to infinity x square upon 1 plus x square dx, and this is surely not convergent. Thus, we can show that higher order moments for a Cauchy distribution do not exist. Hence, moment generating function for Cauchy 1 comma 0 does not exist. However, its characteristic function which is defined as phi x of t is equal to 1 over pi into minus infinity to infinity e to the power I t x upon 1 plus x square dx and I am not computing it, but this converges to e to the power minus modulus of t. Therefore, characteristic function exists, although its moment generating function does not exist. Properties of characteristic function. One, phi 0 is equal to 1 at the point 0, it is 1, which is obvious, that is why I am not doing it. 2, modulus of phi t is less than equal to 1, since modulus of phi t is equal to modulus of minus infinity to infinity e to the power I t x f x dx, which is less than equal to integration minus infinity to infinity modulus of e to the power I t x f x dx, which is equal to minus infinity to infinity f x dx is equal to 1. 3, phi x at t and phi x at minus t are complex conjugates. Phi x of t is equal to expected value of cos t x plus I sin t x is equal to expected value of cos t x plus I times expected value of sin t x. Therefore, phi x t, its conjugate, is equal to expected value of cos t x minus I expected value of sin t x is equal to expected value of cos t x minus I sin t x is equal to expected value of e to the power minus I t x, which is equal to phi x at minus t. Thus, we get the result. 4, phi of a plus b x at t is equal to e to the power I a t into phi x at b t. This is straightforward. And I leave it as an exercise. The next generating function that we study is probability generating function. This is comparatively simple and works for discrete integer value random variables. So, suppose x is a random variable taking values 0, 1, 2, k, like that, and probability of x taking the value I is equal to say p I. Then the probability generating function of x is defined as p x at s is equal to sigma p I s to the power I is equal to 0 to infinity, if it converges for some interval minus s naught less than s naught around 0. Note that if we take s is equal to e to the power t for some t, then p x f s is equal to p x at e to the power t is equal to sigma p k e to the power t k is equal to expected value of e to the power t k is equal to moment generating function of x. Thus, for discrete integer valued random variables, probability generating function and moment generating function are closely related. Now, consider x to be a discrete integer valued random variable. Find PGF of x plus 1 and 2x. PGF of x plus 1 at s is equal to sigma x is equal to 0 to infinity p x into s to the power x plus 1, because x plus 1 takes the value say 5 when x is equal to 4. Therefore, s to the power 5 will be multiplied by the probability of 4. Same is for all x is equal to s times probability generating function of x around the point s. PGF of 2x at a point s is equal to sigma x is equal to 0 to infinity p x into s to the power 2x is equal to sigma p x into a square whole to the power x is equal to PGF of x at the point s square. Similarly, if we need PGF for kx, that is PGF of k times x at a point s is equal to sigma x is equal to 0 to infinity p x into s to the power k x is equal to PGF of x at s to the power k. Now, suppose x is a random variable taking values 0, 1, 2 up to infinity like this. X takes the value 0, 1, 2 k with p 0, p 1, p 2, p k. Consider q k is equal to probability x greater than k. Therefore, q 0 is equal to p 1 plus p 2 plus p 3 up to infinity. q 1 is equal to p 2 plus p 3 up to infinity. q 2 is equal to p 3 plus up to infinity. Like that, if we sum, then we get sigma q I is equal to 0 to infinity is equal to 1 times p 1 plus 2 times p 2 plus 3 times p 3 plus k times p k plus up to infinity. This is nothing but expected value of x. Thus, for discrete integer valued PMFs, we find sigma over x probability x greater than x, x is equal to 0 to infinity is equal to expected value of x. So, this is an interesting property of such variables, but for me, for the time being, we find that another set of probabilities namely q 0, q 1, q 2, q 3 like that. From this sequence of probabilities, we can get another probability generating function, namely q s is equal to sigma q y s to the power I is equal to 0 to infinity. Question is, how are P s and Q s related? That is a very interesting question, and we solve it as follows. Q I is equal to probability x greater than x I. Therefore, P I is equal to probability x greater than x I minus 1 minus probability x greater than x I. Therefore, P s of x is equal to sigma P x s to the power x, x is equal to 0 to infinity is equal to P 0 plus sigma I is equal to 1 to infinity P I s to the power I is equal to P 0 plus sigma I is equal to 1 to infinity Q I minus 1 minus Q I s to the power I is equal to P 0 plus sigma I is equal to 1 to infinity q I minus 1 s to the power I minus sigma I is equal to 1 to infinity q I s to the power I is equal to p 0 plus s sigma I is equal to 1 to infinity q I minus 1 s to the power I minus 1 minus sigma I is equal to 0 to infinity q I s to the power I. Since we have added the terms q 0 s to the power 0, which is q 0 with a minus sign, to compensate we add one q 0 is equal to p 0 plus q 0 plus s times. Now, we understand that since summing from I is equal to 1 to infinity q I minus 1 into s to the power I minus 1, we can write it as j is equal to 0 to infinity q j s to the power j minus sigma q I s to the power I is equal to 0 to infinity is equal to p 0 plus q 0 plus this is q s and this is also q s. So, we can write it as q s into s minus 1. Now, p 0 plus q 0 is equal to p 0 plus probability x greater than 0, which is equal to p 1 plus p 2 plus p 3 up to infinity is equal to 1. Therefore, p s, let me write it as p s is equal to 1 plus q s into s minus 1. Therefore, q s is equal to 1 minus p s upon 1 minus s. So, these two different probability generating functions are related by this relationship. So, this is an interesting generating function, which is comparatively simpler than moment generating function or characteristic function. Let us now see examples of probability generating function. One, Bernoulli distribution. So, suppose x is distributed as Bernoulli P, therefore, P x s at S is equal to q times s to the power 0 plus p times s to the power 1 is equal to q plus p s. Therefore, if p is equal to half, then p x s is equal to half times 1 plus s. On the other hand, if p is equal to say 3 by 4, then p x s is equal to 1 by 4 plus 3 by 4 times s is equal to 1 by 4 into 1 plus 3 s. Binomial distribution with parameters n comma p. Therefore, p x s is equal to sigma x is equal to 0 to n n c x p to the power x q to the power n minus x into s to the power x is equal to sigma x is equal to 0 to n n c x p s to the power x q to the power n minus x, which is equal to q plus p s whole to the power n. Poisson distribution with lambda. Therefore, p x of s is equal to sigma x is equal to 0 to infinity e to the power minus lambda lambda power x upon factorial x into s to the power x, which is equal to e to the power minus lambda sigma x is equal to 0 to infinity lambda s to the power x upon factorial x, which is equal to e to the power minus lambda into e to the power lambda s, which is equal to e to the power minus lambda into 1 minus s. How do we get back our probabilities? P x from the probability generating function P s of x, that is very simple. P x s is equal to P 0 plus P 1 s plus P 2 s square up to say P n s n, P n s to the power n, it may be finite or infinite. Series P prime x at s is equal to P 1 plus 2 P 2 s plus 3 P 3 s square plus 4 P 4 s cube, like that. Now, P x at 0 is equal to P 0 is equal to probability x is equal to 0. P prime x at 0 is equal to P 1 is equal to probability x is equal to 1. P double prime x at 0 is equal to 2 P 2 plus 3 into 2 into P 3 s plus 4 into 3 into P 4 s square plus etcetera at 0 is equal to 2 P 2 is equal to 2 times probability x is equal to 2. Therefore, p double prime x s at 0 is equal to 2 times p 2. In a similar way, the third derivative of probability generating function is equal to 3 into 2 into p 3 plus 4 into 3 into 2 into p 4 s etc. Therefore, p x 3 at 0 is equal to factorial 3 into p 3 is equal to factorial 3 into probability x is equal to 3. In a similar way, we can find the rth derivative of the probability generating function will give us r factorial into probability x is equal to r by setting s is equal to 0. Let us now observe some important properties. P x at s is equal to 1 is equal to p 0 plus p 1 plus p 2 is equal to 1. P prime x at s is equal to 1 is equal to p 1 plus 2 p 2 plus 3 p 3 etc. is equal to expectation of x. Similarly, p double prime x at s is equal to 1 is equal to 2 p 2 plus 3 into 2 into p 3 plus 4 into 3 into p 4 like that is equal to sigma x is equal to 2 to infinity x into x minus 1 into p x, which is equal to expected value of x into x minus 1, which is equal to expected value of x square minus expected value of x. Therefore, p double prime x of s at s is equal to 1 plus p first derivative of x at s is equal to 1 minus p prime x s at s is equal to 1 square is equal to variance of x. I like you to verify these results for different discrete distributions. The last topic on this is called cumulant generating function. The cumulative generating function of a random variable x denoted as k x of t is defined as log of mxt to the base e. That is, it is the natural log of the moment generating function. Since mxt is equal to 1 plus mu 1 prime t plus t square upon factorial 2 mu 2 prime plus t cube upon factorial 3 mu 3 prime, like that. Therefore, what is log of mxt? That is the question. We know natural log of 1 plus x is equal to x minus x square upon 2 plus x cube upon 3 minus x 4 upon 4, etc. Therefore, log of 1 plus mu 1 prime t plus t square upon 2 mu 2 prime plus t cube upon factorial 3 mu 3 prime plus t 4 upon factorial 4 mu 4 prime, etc. is equal to t mu 1 prime plus t square by 2 mu 2 prime plus t cube by factorial 3 mu 3 prime minus half of t mu 1 prime plus t square by 2 mu 2 prime plus t cube by 3 factorial 3 mu 3 prime whole square plus 1 by 3 into t mu 1 prime plus t square by 2 mu 2 prime plus t cube by factorial 3 mu 3 prime whole cube. Like that, we can have the infinite sum. Therefore, to find the cumulant generating function, we need to first understand what is a cumulant. The coefficient of t to the power r upon r factorial in the expansion of kxt, which is equal to log of mxt, is called the rth order cumulant. So, let us write kxt as kxt is equal to k1 times t plus k2 times t square factorial 2 plus k3 times t cube factorial 3 like that, and if we equate this with this expression that we got here, what we are getting is k1 is equal to mu 1 prime, which is the mean, k2 is equal to mu 2 prime minus mu 1 prime square, which is equal to variance, k3 is equal to mu 3 prime minus 3 mu 1 prime mu 2 prime plus 2 mu 1 prime cube, which is equal to the third order central moment, etc. Thus, from the cubular generating function also we can get moments of different orders. So, before I stop, I give you small examples. Normal mu sigma square, therefore, mxt is equal to e to the power mu t plus half sigma square t square. Therefore, kxt is equal to mu t plus half sigma square t square. Therefore, k1t is equal to mu, k2t is equal to sigma square, krt is equal to 0 or greater than 2. Similarly, another example, say gamma with 1 comma alpha. Therefore, mgf is equal to 1 upon 1 minus t whole to the power minus alpha. Therefore, log of mxt is equal to minus alpha into log of 1 minus t is equal to minus alpha into minus t square by 2 minus t cube by 3 is equal to alpha times t plus t square by 2 plus t cube by 3, etc. Therefore, k1 t is equal to alpha, k2 t is equal to alpha, k3 t is equal to 2 alpha, k4 t is equal to 6 alpha, etc. This is very simple, because you have to consider the coefficient of t to the power r upon factorial r, and to compensate for that factorial we need these extra coefficients. Okay, friends, I stop here today. In the next class, we shall discuss an important concept of probability, which is called Poisson process. Typically, this is used for modeling an arrival process that is when a number of arrivals are there at some point, how to estimate the time required for k many arrivals on the average, where k can be 0, 1, 2, etc. Also, we shall discover the relationship between exponential distribution or gamma distribution in a more generalized way and Poisson distribution. Thank you so much.